Okay, 350. Welcome to recitation number 8. In recitation 8, we're going to go back over some stuff we kind of left off towards the end of recitation 7. So we're going to revisit concurrency, talk more in depth about it, give you an example of what concurrency would look like on FreeRTOS, which is what the new lab's going to be working with. And then kind of just try and prep you for the quiz that will be on Friday. So just as a reminder, since we pushed back the Gamulator lab from last Friday to this coming Friday, that means you're going to have the concurrency worksheet, the Gamulator lab, and a quiz due all on the same day. So just as that's probably gonna be one hectic day. Please, please, please get the Gamulator lab done first if you're trying to figure out how to prioritize things. The concurrency worksheet is relatively straightforward after this recitation, hopefully, and then the ESC, the quiz is going to be on RTOS and concurrency material in addition to any material related to the past couple of labs. Generally, we're just going to be focusing on RTOS and concurrency, though. So without further ado, let's get back to where you were on recitation 7. So recitation 7, we were talking about concurrency in terms of what it means for multiple tasks. So just as a reminder, we use these words task, threads, processes, kind of interchangeably, and I just want to make sure that we're comfortable with these definitions. So a task, a thread, and a process. So a task is an RTOS term for a periodic event that has an execution, a period, and a deadline. So tasks are normally referred to in RTOS because we're talking about how do we schedule tasks, how do tasks execute in tandem with one another. Tasks can be concurrent. You can have concurrency issues with tasks, but we normally tasks don't tell you too much about lower level implementations. So then we have thread and process. These are OS terms. Okay, my pen's not drawing the O there, but that's say OS terms. And then a task is an RTOS term. So a thread in a process, a thread is normally how tasks are implemented. And a thread is, you can kind of think about it as you have your program, and your program has multiple things happening simultaneously. We could have, you kind of have what we refer to as your main thread, which is how most of you, if you've never done concurrent programming before, you're probably writing all of your stuff you write, unless you make another thread, everything you do happens in your main thread. And then when you spawn or you create or you just create a new set of threads, that is a new thread, but that's still associated with your program. And what I mean when I say program is it's your program process. So multiple threads exist in a process. What is a process? Well, simplest example would be, let's see, I have a couple things on my hotbar. Let's open up something that will like this. So I have putty, but I can also do another version of putty. These are two instances of putty. They're, except for a couple contention problems in terms of them both trying to maybe use the same port, I can interact with the settings on one, interact with the settings on the other. They don't necessarily affect each other until they do, maybe if they save their state to a file or if they load from a file. I can click between these tabs and it doesn't really affect the other one. These are two different programs. They're the same code, but it's two different instances of a program, and we call this two processes. And if we have two processes, it looks like this. We have process 1. We have process 2. And we can have these two processes be the same underlying code base, and they can execute in tandem, and there's not really an issue with that. And it's not really, concurrency tends to not get brought up until you get into the issues associated with concurrency. And the main issues associated with concurrency are related to communication. So I can run multiple versions of PuTTY. The person who made PuTTY probably didn't have to think too heavily about that. But what's another example of something I could have multiple instances of that, would actually talk to one another on a computer? Well, if I open up Visual Studio Code, I should have this program. So this is a program I was working on earlier. It's a point-to-point conversion program. And the basic gist of how this works is, let's see. Let's see if I can explain it. So the way the point-to-point converter works in practice is I have this program that's executing in Unity. That's the main application. And I have this slow process that I need to do, this slow kind of calculation. And due to complications associated with Unity's compiler, it relies on libraries that are not compatible with Unity. So I have all of the calculations being done in an external program running simultaneous to the Unity instance. And whenever I need to calculate certain things, I have this pipe, which I receive from, and I'm able to read and write from the pipe and do my calculations. Based on, I'll get arguments from the pipe, and I'll send the results back. So in my instance, I have one pipe going from process A to process B, sending args, and another pipe sending return values. And this is an example how two processes could communicate. So this is on one computer. This is me just using pipes. But another way you could do this is if you had multiple computers, you could have two processes exist on two separate computers. I'll call this one P1 and this one P2. And I could have these two processes exist on two different computers, and I'm going to have them communicate one to another. And the act of them communicating, instead of being done over a pipe, which is an OS term for two processes under the same operating system communicating to one another, I could have them communicating over a socket, which is similar to a pipe, except it goes between two different computers, two different operating systems. And sockets are how you can have UDP sockets, you can have TCP sockets. They're the basis of HTTP protocol, which is what allows us to have nice web pages that are rendered. And that's how processes communicate. And anything related, there are a couple other ways you can get them to communicate. Shared memory is another example. But all of these fall under what's called IPC, or inter-process communication. And IPC is a beautiful overarching term. It has a host of concurrency issues associated with it. But what we're focusing on for this class is actually not concurrency between processes. We're talking about concurrency with threads. And this is actually much simpler than inter-process communication. So in inter-process communication, you generally have some server, even if it's IPC with pipes, you generally have some process that has some client process that has initiated the communication with this server process, and the server process was waiting on a communication to begin, and the client process will start the communication, connect to the server process will respond, and maybe that's one and done, maybe it keeps up, but you have this client-server architecture. When you talk between threads, it's actually significantly simpler, because if you remember from last recitation, we have, your process, each instance of a process has associated with it data, code, a heap, and it has a stack. The only thing in here that changes when we have another thread is we get a different stack. So you can have two stacks at the same time. And the only difference is you have two stacks and you have two separate program counters. You have your PC thread 1 and you have your PC. I'm pointing the wrong part. Thread 2. PC thread 1 is going to point to here in code. PC thread 2 is going to point to here in code. So they can execute different parts of the code, but the code's still the same. The heap is still the same. The static data is still the same. So we can communicate through heap data, static data, stuff like that. That's how we can keep shared values. And so when we're dealing with this, if we have two separate threads, each of which are changing the same part of heap data or the same part of static data, we're going to want to have some way of mitigating two threads concurrently, where the OS is constantly context swapping between them. We want to stop these two threads from doing anything that was not intended. One example of this is, and I'll this is kind of a demo example, please. So this won't actually run, but the classic example is you have int main. I'm going to say void foo. And there's going to be the static int count. And all void foo is going to do is it's going to for int I equals 0, I is less than 1,000, I plus plus, count plus plus. So I'm going to do new thread foo, Um, and I'm going to do another new thread, T2, and then I'm going to do T1 join, T2 join, printf, count. And the question I have for you, and you can stop this and consider it for, but what is printed out? Is it going to be 1,000 that gets printed out? Is it going to be 0 that gets printed out? Is it going to be 2,000 that gets printed out? And the answer is it could be realistically quite a large number of things. It could be anything between 1 and 2,000. And the reason for that is if these threads execute in serial, and by serial I mean T1 executes to completion, stops, and then T2 executes to completion and then stops. Well, the behavior you'd expect is that foo increments count 1,000 times. So you'd expect count to be 1,000 at the end of T1 and 1,000 plus 1,000 or 2,000 at the end of T2. The issue with this is that's only one possibility. Threads can interrupt each other. Threads can just context swap at any random point in time. And it's if you're not dealing with a really transparent scheduler, especially on non-RTOSs, this is basically non-deterministic. You have no clue what's going to happen, and you have to plan for every possibility. So one execution of this would be thread 1 executes the for loop over and over and over again, and it gets to I equals, let's see, so T1 gets to I equals 999. And so what ends up happening there is it's going to do count and count. If you remember, we've done count before. It's an incrementation operation. So really what that's doing is it's taking this temp, it's saying count is equal to, load count into temp. Increment temp store temp at count. And this is kind of how the incrementation operation works. So if I equals 999, and then let's say we context swap to thread 2, we're going to, thread 2's first operation is it's going to load count into temp. Well, we can get around this. Let's say thread 2 starts off. I know I'm kind of going in circles. Apologize. But let's say thread 2 starts and its first operation completes. So it's gonna start, load count into temp. It's going to get part way through its first operation. Context swap to T1. Now we're going to have T2 increment and store temp to count. Context swap to T1, load count, context swap to T2, finish everything, context swap to T1. And so as you can see here, if you look through it, if you do it in this order, T2 will be storing 1. It will store 1 in its register. We'll have 1 in its register. We'll go to T1, get T1 almost finished, just its last lap. T2 will context swap, store, basically override everything that T1's done up until this point, and just store 1 as the value of count. At which point T1 will load count and store the 1 in its register, and right before it increments that value, T2 will take over, complete, and then T1 will come back and take its register value. At this point in time, count's probably 1,000. It's going to take its stored register value, which was the last time it saw count, and that was when it was 1, and it's going to increment that, have 2, store 2 in the actual address of count, and that's what's going to happen. And the end value is that 2 will be printed because thread 1 and thread 2 will execute like that. So this is kind of the issue with having 2 separate threads jumping back and forth between each other from time to time. Concurrency creates multiple issues like this. So our solution is we want to make sure we can make sure that, while you're incrementing is a series of operations, and we want to make sure that while this is happening, no thread can stop and just make sure it doesn't it context swaps, changes the underlying value, comes back in, and next thing you know, you get this like it read the value, but it wasn't the value that it thought it was, and when it stored it, the underlying value it was storing to changed. The way we get around this is we use a semaphore or a mutex. So all this is basically pseudocode. So I'm just going to use static std mutex, and I'm just going to say my lock. I'm just going to do my lock.lock, my lock.release. And the effect that this has is that anytime someone wants to increment, the first thing they have to do is they have to acquire the lock. And if they don't have the lock, they tell the scheduler will just go to another task, and you get this pattern of the scheduler just checking, oh, you're waiting on the lock, I won't schedule you, I will only schedule you once the lock has been released and I can actually assign it to someone else. So the effect of this is that thread 1, maybe that gets started, it gets the lock for the first count, and thread 2, right off the bat, it can't interrupt it while it's incrementing. What it can do is it can interrupt between increments because we haven't locked outside the for loop, but that has no effect because what we're worried about is not that the counts will interleave. What we're worried about is that internal to the counts they will interleave. We have this critical section problem. And let me clarify what I mean by that. This, if we were to bump the lock outside the for loop, that would accomplish the exact same thing in terms of the end result as putting it inside the for loop, except now whichever thread starts has to complete entirely before the other thread can take hold. And this is not ideal if we're doing something like writing for multiple cores. Processors have multiple cores associated with them. This is my bad drawing of a CPU, but this is very unrealistic as to what it looks like under the hood. But processors have multiple cores. Each core is simultaneously trying to access and do these calculations for all of the processes that are occurring. If you have kernel level threads, which are threads that the OS knows about, and it can schedule the threads instead of having user level threads where the libraries of the programs are doing the thread management. A kernel level thread can have one thread running here, one thread running here, maybe a program 3 running here, program 4 running here. Um, if you have something like that, there might be this incentive to move the locks inside the for loop, because in that case, we can have, sorry, we can maybe do a print statement here. We can do extra stuff here, and while these unimportant, not critical section centric pieces of code are executing, we can interleave them. Maybe this is executing its print statements while this one's doing the incrementation, and then they swap, they trade off. And we can still get the benefit of doing this parallelized processing instead of having to do it back to back in this serial fashion. Doing things in a serial fashion, if you put a critical section around everything and you said, I'm just going to lock mutex at the beginning of everything, that would work perfectly fine. But what you're going to end up seeing is that mutexes have this benefit where if we explicitly say the things that are critical sections and we make them small and narrow enough, we can get a speed boost that might be necessary or in some cases. So that's just why you would want to lock and why we kind of want to keep them small. So now I'm going to move on to, we had this ATM problem from last week. We gave you kind of the naive version, how you would do it without locks. We talked about how, this balance, this idea of like an account has a balance. That's this variable that we're editing in both cases. We're incrementing and decrementing. These incrementation and decrementation operations are actually multiple lines of assembly. They're not atomic, so we could hop back and forth in between them, and we don't want interleaving of the assembly like that. So we add these locks to kind of create these critical sections that are protected. And that's kind of our fixed version. What I want to go ahead and show you is, if I get it correct, let me see. I think my mouse is messing up, but what I want to go ahead and show you is some FreeRTOS code that would accomplish this. So we can begin to get ready for the lab that's coming up, and you can begin to get comfortable writing FreeRTOS. So FreeRTOS is a nice library for scheduling real-time operating system tasks. You can compile it to many microcontrollers. Another thing that FreeRTOS has that's very nice is there is a version of FreeRTOS that runs on Windows, so you can develop on the Windows side, port it to any of your microcontrollers relatively easily. It makes it very nice if you want to have sort of code that's microcontroller independent. So I'm going to go ahead and get started. When you open up FreeRTOS for Windows, you'll have, if I do this correctly, you'll have FreeRTOS as a zip folder for the lab. You'll unzip it, navigate through this, go to FreeRTOS, demo. These are all the processors that are supported. Scroll down to Win32, Microsoft Visuals. And then we're going to go on and click the VCX project, and that's how we're going to open up it in Windows Studio. You can also click the solution file, basically the same thing. From there, if you're not using a Windows computer that you have access to that has a version of Visual Studio's 2019 on it, we do have Visual Studio's 2017 available on the virtual labs for Cs. The thing you'll have to do is you'll have to go to Project, do Properties, change Platform Toolset from V142 to V141. You'll just click this down, V141 will be right there, and then you'll click Apply. Since I'm on Visual Studio's 2019, I don't have to worry about that. Your Solution Explorer probably won't pop up immediately, but to do that, you just have to click Control-Alt-L or click View in Solution Explorer, and that will pop this up. You'll do RTOS demo, demo app source. Main is the file that launches everything. What you're going to be editing will be under Blinky demo main.blinky. When you get FreeRTOS up and running initially, you'll be able to just click local Windows debugger and it will show you a demo where it has a print statement being printed by you're going to have a send task and a release task, and they're going to be communicating via blocked queue, sending messages down the blocked queue from the send task to the release task to notify it. And then you're also going to have a timer task that is going to have an initial delay, and then after a certain delay, it's going to fire off once and only once, and then terminate. And that demo should be pretty straightforward. You should be able to just press local Windows debugger, and it should run to completion, build, be relatively straightforward. For today, I'm going to walk over a couple examples in FreeRTOS that are slightly different than the initial stuff they give you. So we're going to start by looking at, and I'm just going to define this. We're going to start by looking at a working version of the banker's problem, the ATM problem. So initially what we're just going to have is we're going to have this function. So we're going to have two tasks. When you run FreeRTOS main_blinky.c, the first thing it's going to run is main blinky. So we're going to have main blinky, and main blinky is going to create a mutex because we need a mutex. It's going to see if the mutex has been successfully created, and if that's true, it's going to create two tasks. You're going to have withdraw 100 and withdraw and deposit 200. And these are the two tasks that are going to run concurrently. FreeRTOS is nice in that it allows you to configure all these different things. It will refer to your task in debug statements based on whether or not you launch as verbose or not. It's going to refer to it by this nice name you give it. It's going to have a certain amount of stack space. This, I believe, xtask create, if I remember correctly, some of these FreeRTOS functions are macros, and the reason they're macros is so that the compiler can do some allocation at compile time. This might be an actual function, and then you can optionally send certain functions parameters. If you give them parameters, it's going to be an array of void pointers, so keep that in mind. If you give it some structure in the parameter, you're going to have to cast that structure on it, and then it has a priority associated with it. I just gave these two tasks one above the idle priority. You can give it the idle priority. Priority doesn't matter too much as long as it is either idle or above. So this is us creating the withdraw task. The deposit task is identical. We're just giving a different name and a different task handler. The task handlers are these static void functions that take in a void pointer. That is the parameter. So none of the parameters are being used. I'm just using this void casting in order to suppress the compiler's output that I'm not using the parameters provided. It will give some warnings if I don't. And we're just doing the same thing. I'm going to deposit 200. I'm going to withdraw 100. These are just going to be executed by the scheduler in some sort of non-deterministic way. The reason they're non-deterministic is because both of these tasks have identical priorities. And what's going to happen is FreeRTOS is going to, by default, time slice processes of the same priority. What this means is if you do RMA, rate monotonic, FreeRTOS actually will do this sort of rate monotonic thing where higher priority tasks need to yield to lower priority tasks, or they need to be blocked in some fashion in order for lower priority tasks to take precedent. That being said, two tasks of identical priority execute in a round-robin fashion, whereby the task will go for a certain amount of time until it calls an OS call or tick has been executed. In the OS, the FreeRTOS will just say, okay, I'm going to skip this task and go to the next task of the same priority. It's just going to go through different tasks. This is non-deterministic, and the frequency at which it changes will vary. While you might not see a concurrency issue with FreeRTOS, like for example, if I get rid of these semaphores, I probably will not see a concurrency issue. If you make the critical section large enough, you will see a concurrency issue with FreeRTOS. And so it's very important to use semaphores and mutexes to denote that when it needs to happen. So I'm just going to go ahead and run this. I have all this code working. What we expect to see is that it's going to withdraw a certain amount of money, and the balance is going to be just the basic math going forward. If it withdraws 100 from 0, the balance after withdrawal should be negative 100, and this makes sense. Withdrawing 100 from 0, balance is negative 100. Depositing 200 to something with negative 100, balance is 100. That makes sense. That's exactly what we want. So we're achieving that with these mutexes. In FreeRTOS, you have FreeRTOS, mutex. You have this interesting situation, which is a mutex for FreeRTOS is implemented as a variant of a semaphore. You also have binary semaphores. If you remember from last recitation, I discussed that binary semaphores are not the same thing as mutexes. This is an example where that's actually the case, because what's happening is a binary semaphore, a mutex can be locked and unlocked, and a binary semaphore can be locked and unlocked. The difference here is a binary semaphore can be locked and unlocked by another. It can be locked by one task and unlocked by another task. A mutex for FreeRTOS has to be unlocked by the task that locked it. So it has this notion of ownership that is not present in binary semaphores. I just want to make that clear in case you're implementing the lab and you're wondering, why does it fail whenever I try to unlock a mutex? Well, were you the process that locked it in the first place? We'll get into later how you would do some stuff. Okay, so now we're actually going to go ahead and do it. So that's the withdraw example. So I was just discussing what would happen if you had, a binary semaphore. Why would you ever want that behavior? And the answer is because you can use it kind of as a signal. You can have two tasks that are executing simultaneously, have one task wait to acquire a semaphore, and have the other task give the permission that the semaphore can increment. This, while it is still being used as this kind of concurrency thing, it's no longer being used as a it's not really being used as like this resource to protect a critical section. Instead, it's being used more like a signal. It's being used to notify another task that it can proceed. In this situation, it's almost identical, except instead of having withdraw and deposit, we have sender and receiver, and they're agreeing on this binary semaphore, which is a counting semaphore initialized with a max of 1 and a initial value of 0. And we still have similar task priorities and all that. And the sender is going to send the signal. It's going to make it so the semaphore is in a available state, and the receiver, whenever it gets to the semaphore take function, is going to check, can I take the semaphore? If so, grab it. One thing you might notice is I have this kind of parameter called port delay, and it's max port delay. What I'm doing there is The semaphore take function for FreeRTOS, by default, it accepts an argument in there that says how long are you willing to wait on this semaphore. So if it takes a very long period of time to wait on a semaphore, maybe you might have another function kick in. Um, for your lab coming up, you're going to want to wait indefinitely. So I have port max delay, and the other thing that's very important is you need to define include v task suspend, which means you are able to suspend the task and do absolutely nothing for an indefinite period of time. So I'm just going to go ahead and run this. What I expect to see is, the sending task is not waiting on anything. It can continue sending over and over and over again. The receiver doesn't have to receive, but it can continue sending, and the receiver will receive once, and it will have to have at least one sending task execution, one loop through the sending task to have the ability to receive again. So the receiver can't receive multiple times because we have this binary semaphore that can't cache more than one value. Because if you look, we put a max on it. So its maximum count is 1. It can't have any more than one resource. So if we do this, I'm just clicking local Windows debugger. It's going to take a little bit of time to run. And I'll pause this just so we can look at the output. So we see it's sending, it's receiving. The one thing I will warn you about this is don't always trust when you're dealing with concurrency issues. We can logically understand that this receiver needs to take the semaphore before it can come back. You might notice here it says receiving. That logically can't happen, that the receiver is going through twice and the sender doesn't get to execute. What's more likely happening has to do with the print statement being received by the other task and how the print statement is processed. So print statements are kind of deceptive. If we think back to how you did ISRs and stuff like that, don't always trust what print statements say. They're not always reflective of what's actually happening with multiple concurrent processes. This is kind of because it's not easy to serialize these processes, and the print statements are just being output by whatever order the OS receives these functions. So for example, I could do sending, signal sent. Sent and sending don't always have to appear next to one another. You can get some weird operations in there. So without further ado, let's look at the final one. So you may have talked in class about the producer-consumer problem. The producer-consumer problem is this idea that you have maybe one person. It's been called the producer-consumer problem, the reader-writer problem. My take on this is right now we're dealing the baker problem. So there's a baker and there's someone who's eating all the bread. You have your baker customer, and the baker will bake a dozen loaves, and then the customer will come in and eat loaves one at a time, and then once they've consumed all the loaves, the baker needs to be told, okay, now bake all these loaves. In this example of producer-consumer problem, I want to clarify this implementation would not necessarily work for a situation where there are multiple consumers, and that's kind of the generic reader-writer problem that we talk about that you should have in the concurrency worksheet. So please don't look at this and think, oh, obviously this is how you would implement reader-writer. There are some issues when you have multiple consumers where maybe there is a fixed, maybe all the consumers need to consume and then the producer can produce. And you have to have this idea of like, what happens when you're the first consumer? How do you stop the producer if you're the first consumer? If you're you're not the last consumer, but you're a consumer who wasn't first, what do you have to do? And then if you're the last consumer, what operations do you have to do? So there are these concurrency issues, and I'd like you to think about it. Ideally, you should have, um, a couple general cases, what needs to be done for any consumer, what needs to be done specifically for the first one, what needs to be done specifically for the last one. Those are normally issues with the producer-consumer problem, but we're just going to walk through this. So my version of the producer-consumer problem has two semaphores acting as, these are binary semaphores, they're acting as signals to show there's a full signal. So the full signal is being sent from the producer to the consumer when they've made a baker's dozen worth of loaves, and then they sit back and wait. And then the consumer will send the empty signal when they've consumed all 13 loaves of bread. And then you have this mutex for critical sections, and that's just protecting this critical section is just here to make sure that this can't possibly be executed at the same time as other things. In this situation, I should be able to see, gives full signal. I take full signal. It takes the empty signal, waits. In this situation, if I'm only doing one producer and one consumer, I should be able to exit. I should be able to remove these critical sections, but the critical sections do come into play when you deal with multiple producers and consumers, as they make sure that two can't execute at the same time. And one of the important things if you dealt with multiple is you'd want to make sure that you're sending or you're taking multiple empty signals or multiple full signals. And these would have to be upgraded from binary to full counting semaphores with your values. You can look into this if you just go to the producer-consumer Wikipedia page. It's relatively straightforward. And so I'm just going to run this, and what I'm expecting to see is that, producer makes a baker's dozen, the consumer consumes a baker's dozen, and it goes back and forth and back and forth. So if I pause at any point in time, I should be able to see, yes, the baker bakes some loaves, all 13 loaves are consumed, baker bakes some loaves, and it goes back in this cyclical fashion. So as you've seen up until now, we can kind of use semaphores and mutexes in two kind of ways. They can be used to denote, you can use a mutex to denote that I have this critical section and I don't want anything entering this critical section. You can surround it by I lock the mutex, I release the mutex, and you can have every single thread that does the same kind of like operation on the same set of variables can have these critical sections around them. Semaphores are more useful in certain situations where you have another process locking and a different process releasing. Or if you want to have a critical section and say, maybe I'm doing a critical section like a mutex, but I want to allow a certain amount that's not just one thread execute in that critical section at the same time. So maybe you want a couple to be executed at the same time, but not only one. So this is just going through FreeRTOS. I'll define that. The code for the version of the ATM problem should be at the end of your recitation sheet, showing how I set that up. As a reminder, Friday is a quiz. It is the Gamulator lab, and it is a worksheet, which is your concurrency worksheet. I don't have anything else today. Our next recitation will be jumping away from all of this concurrency stuff and going straight to controls, feedback, ideas about controls, and more specifically, the PID controller, or the proportional, integral, and derivative controller. So we'll be looking at a system where you have inputs U, we're going to have a state X, we're going to have an output Y, and we're just going to have a sensor, which gives a Y of t that is expected, and that's going to feed into this error term where we have a reference y of t is going to be minus 1, and that's going to add in to be an error term, which will take place for our input in the system. So we're going to have this error that's going to feed back into our system. Systems have state, they give out an output. We're going to have this loop. Generically speaking, systems have a u of t, or an input. They're described, they have an x of t, and they have a y of t. Or formally speaking, y is equal to x of t, u of t. And then we're going to be applying controls to that. We'll have Q&A tomorrow regarding the recitation video. Please hop on if you have questions about recitation. I can also go over any questions regarding the Game Emulator Lab. By now, with the Game Emulator Lab, given how much time you have left, I'd recommend you should probably, at least by Wednesday, be at a point where all you have left is doing rendering to the screen and maybe some timers. You really want to finish up on those non-input-output assembly instructions as quickly as possible, and then get to a point where all you have to do is draw pixels to the screen. Anyway, C350, remember to like and subscribe.